Semiconductors are the unsung heroes of the modern world. They form the backbone of countless electronic devices that shape our lives. From smartphones and computers to solar panels and medical equipment, semiconductors are essential components that enable technological advancements across various fields. Their ability to control electrical current has revolutionized communication, computation, and energy generation. Understanding the physics behind these remarkable materials unlocks a deeper appreciation for the intricate workings of our technological world and paves the way for future innovations.
At the heart of semiconductor physics lies the concept of band theory, a fundamental principle that helps us understand the electronic properties of materials. This theory explains the behavior of electrons within materials by considering the energy levels they can occupy, and how these levels are structured within the material. Imagine electrons as occupants of an apartment building, with each floor representing an energy level. The electrons can move between these floors, but only under certain conditions. The ground floor represents the lowest energy level, called the valence band, while higher floors represent higher energy levels, culminating in the conduction band. Electrons need energy to move from the valence band to the conduction band. The crucial difference between conductors, semiconductors, and insulators lies in the gap between the valence and conduction bands, known as the band gap energy. This gap determines how easily electrons can move between these bands. In conductors, these bands overlap, allowing electrons to move freely like residents moving between floors without restriction. This free movement of electrons is what makes conductors so effective at carrying electric current. Insulators, on the other hand, have a large band gap, making it difficult for electrons to jump to higher energy levels, much like a tall building with no stairs or elevators. This large gap prevents the free flow of electrons, making insulators poor conductors of electricity.
Semiconductors occupy a fascinating middle ground. Their band gap is small but not non-existent. Think of a building with a few flights of stairs between floors. With a little bit of energy, electrons can jump from the valence band to the conduction band, enabling them to conduct electricity. This unique property makes semiconductors incredibly versatile. By controlling the number of electrons that can make this jump, we can manipulate the flow of current and create electronic devices.
To further understand electron behavior, we introduce the concept of the Fermi level. Imagine the Fermi level as a line drawn through our apartment building representing the highest occupied energy level at absolute zero temperature. In metals, where electrons flow freely, the Fermi level lies within the conduction band, indicating that electrons are always available to conduct electricity. It's like having some apartments on the higher floors always occupied, ensuring a constant flow of residents. The Fermi energy, closely related to the Fermi level, represents the energy of the highest occupied state at absolute zero. In metals, it's a measure of the kinetic energy of the most energetic electrons. Think of it as the speed limit for electrons in the metal. As temperatures rise above absolute zero, things get a bit more dynamic. Electrons, like restless residents, can gain thermal energy and jump to higher energy levels, even above the Fermi level. The Fermi-Dirac distribution function describes the probability of finding an electron at a particular energy level at a given temperature. It's like a census of our apartment building telling us the likelihood of finding an occupant on each floor. At absolute zero, the distribution is a sharp step function, with all levels below the Fermi level occupied and all above empty. As temperature increases, the distribution smoothens out, with some electrons occupying levels above the Fermi level. It's like some residents venturing to higher floors as the weather warms up. Intrinsic and extrinsic semiconductors. Semiconductors, with their small band gap, exhibit interesting behavior depending on the presence of impurities. Intrinsic semiconductors are pure, with no intentional impurities. Their Fermi level lies approximately in the middle of the band gap, indicating an equal number of electrons in the conduction band and holes, missing electrons, in the valence band.
So, if I understand correctly, extrinsic semiconductors are intentionally doped with impurities to alter their electrical properties?
Exactly. N-type semiconductors are doped with donor impurities which donate extra electrons, pushing the Fermi level closer to the conduction band and increasing electron concentration. On the other hand, P-type semiconductors are doped with acceptor impurities which create holes by accepting electrons, moving the Fermi level closer to the valence band and increasing hole concentration.
the PN junction diode. The magic of semiconductors truly shines in the PN junction diode, a fundamental building block of modern electronics. It's created by joining a p-type semiconductor with an n-type semiconductor. This junction creates a depletion region, where electrons from the n-type side recombine with holes from the p-type side, leaving behind a region depleted of charge carriers. This region acts as a barrier to further current flow. Applying a voltage across the junction can either enhance or overcome this barrier. Forward bias reduces the barrier, allowing current to flow, while reverse bias increases the barrier, blocking current flow. This remarkable property allows diodes to act as one-way valves for electrical current, forming the basis for rectifiers, LEDs, and countless other electronic components.
Solar cells, harnessing the power of light. Solar cells are a prime example of how we can harness the unique properties of semiconductors to address global energy challenges. By converting sunlight directly into electricity, they offer a sustainable solution to our growing energy needs. These devices convert light energy directly into electrical energy, offering a clean and renewable alternative to fossil fuels. This process not only reduces our carbon footprint, but also helps in mitigating climate change. A typical solar cell consists of a PN junction, which is crucial for its operation. When sunlight strikes the cell, photons can excite electrons in the semiconductor material, causing them to jump from the valence band to the conduction band. This excitation is the first step in the generation of electrical energy. This process generates electron-hole pairs, which are essential for the creation of an electric current. The PN junction acts as a built-in electric field, separating these pairs and driving electrons through an external circuit, generating electrical current. This movement of electrons is what powers our devices and homes. The efficiency of a solar cell, a measure of its ability to convert sunlight into electricity, is determined by factors like the material's band gap, light absorption, and charge carrier recombination rates. Researchers are constantly working to improve these factors to make solar cells more efficient. The IV characteristics of a solar cell, which plot current versus voltage, provide crucial information about its performance. These characteristics help in understanding how well a solar cell can convert sunlight into usable electrical energy. Key parameters include short circuit current, open circuit voltage, maximum power point, and fill factor. These parameters are essential for evaluating the efficiency and effectiveness of a solar cell in real-world applications.
The Hall effect and its applications. This section delves into the intriguing world of the Hall effect, a phenomenon that has revolutionized our understanding of electrical properties in materials. The Hall effect, discovered by Edwin Hall in 1879, is a fascinating phenomenon observed in conductors and semiconductors. Edwin Hall's work laid the foundation for numerous technological advancements. When a magnetic field is applied perpendicular to a current flowing through a material, a voltage difference, known as the Hall voltage, develops across the material perpendicular to both the current and the magnetic field. This effect arises from the Lorentz force acting on the moving charge carriers, causing them to accumulate on one side of the material, creating a measurable voltage difference.
The Hall effect has significant applications in sensor technology, particularly in measuring magnetic fields and determining charge carrier concentrations in materials. Hall effect sensors are used in various devices, including speedometers, proximity sensors, and current sensors, providing accurate and reliable measurements. For example, a semiconductor sample with a Hall coefficient helps us understand the behavior of charge carriers within the material. Using the formula R_H equals 1 over NE, we can calculate the charge carrier concentration, essential for designing and optimizing semiconductor devices.
The world of semiconductors is full of wonder and potential, enabling the creation of smaller, faster, and more efficient devices. By understanding their fundamental properties and harnessing their unique capabilities, we continue to drive technological advancements that shape our world. From powering our devices to illuminating our homes with clean energy, semiconductors play a vital role in shaping a brighter future.